All right. So here's the plan for today. I'd like to take a day. I promised yesterday that we would take some time to answer some homework questions and do some other things. So I think we're just going to spend today like cleaning up a little bit. We'll go through an example that we didn't quite finish yesterday. We'll whatever we need to do. So and so maybe as I'm going over this and as we're talking about this problem, you're already readying questions that you might have from stuff we haven't cleaned up. I know from homework 5, the book homework, you had some questions about some of you had some questions about the last couple exercises on homework 5 from the book on parametric equations. I think it was like restricting t to certain quadrants, or restricting it so that we get only in certain quadrants or something like that. So we can look at that, for example. Anyway, I don't have much more to say about this process of finding the intersection between two lines. If I gave you t and t, then you understand that you might want to swap one of them for s, or you could call one t1 and one t2 or something like that. And then can someone just remind us, because the other thing we haven't done in front of you, which we could do, maybe would be worth doing, is to experience this process where in the end they don't intersect. And can someone just remind us, how does that feel? If you did that, what happens? Like, it feels all the same except, can you flesh that out? Like, what happens if they don't intersect? How does that feel as we're doing the process?
How's your day?
No, I don't mean like emotionally. I mean like what happens?
It'll be like down equals negative.
So like you proceed in the same manner. You set these equal to each other. Do you get an s and a t value?
Yes.
You actually will, and for those two values, your lines, when you plug in 2 and 3 to your lines, you'll get for x and for y, if you did all your algebra correctly, you'll get the same thing if you set up your system in the way we did. Maybe you use the first set of equations. But when you go to plug in 2 and 3 into these lines, you'll get different z values maybe, right? Unless you use that equation, in which case maybe you'll get a different x value or a different y value or something. But if you use the first two equations like like Rosa did, or like maybe you did, I assume you used the first two equations, right? Yeah, so she didn't even use this third one, right? She didn't even use the third one. She just, at the end, checked to make sure it actually was right. Does that make sense? That's a critical piece. Everything would have gone really well for her, and then she would have been like, yay! But if she didn't check, it would be very dangerous, because it might be that z is not matching. So there's a homework problem, too, that reminds me of, that we asked, like, here's a line, and then we said, here's a point. Is this point on the line? That was like at the bottom of the first page of the homework worksheet. Does it make sense how to do that? It feels similar. You might want to like find the t value that makes it work, and then see that it works for x, y, and z. I think on that particular problem, the answer is no, it isn't on the line. But you have to check kind of in the same way. Does it work? If you plug in the parameter, do you get the same value that we claimed is on the line? So we can go through those some more if you like to see another example of this kind of stuff. We can. That'd be a fine thing to do. The other thing I asked you is this extra challenge question right here, and maybe we won't go through it completely, but let's at least kind of like say something about how you might do it. And I don't know, did someone actually do it out there? You actually had some success? Okay, let me, how do I do this? Screen, white screen. Okay, so the point that we just got was what? 2, -1, 2? Am I right? 2, -1, 2 is a point, the point of intersection. So the line, I asked you to find the line passing through the intersection. Perpendicular, so that we have like a position, we have a point that we already know on this line. We just need a direction vector, because, and I'm claiming I'd like it to be perpendicular to both lines. Okay, so now the big reveal. How do you get that to happen? You guys seem excited about this over there. Go ahead. Okay, and the two vectors we're interested in are the, what are they?
They are -2, 3, 0, and 1, -4, 2.
Okay, and that is, what are those vectors? Those are the, from the two lines originally. Those are the direction vectors for our original two lines, I assume. Or is that what we got? I just trusted you. And when you did the cross product, I'm also going to trust you. I'm also going to trust you on this. What do you get?
One instead of the wrong. We actually,
Uh-oh.
yeah, not the direction vectors, but we simplify it and add the two together. So, yeah.
Oh, okay. No, we need the direction vectors. Sorry. Okay. So what are the two direction vectors? Just let's copy them from the previous slide. What are the two direction vectors? No, it's gone. 2, -1, -2, 1, and 1, 3, 4. Okay, and we get as our cross product something. I don't know what. Why do we need a cross product? I mean, your reasoning maybe can help us still here, though. Yes, we have two direction vectors, and we'd like another direction vector for our new line that is perpendicular to both of the others. And that's what the cross product will give us, is another vector perpendicular to both of these original vectors. And if you doubt that, remember, you can check by taking the dot product of our result with either of these, and you'll see it's 0. All right, so what do we get? Anyone doing the cross product out there? Someone do the cross product. If I beat you by doing it in my head, then shame on you. Okay. -11, right? -7. Check my work. I mean, actually write it all out and check my work, please. 6. 8. Can someone check me on this, please?
Yeah.
Okay. All right. That's a chore to do in my head, but remember to minus the middle one, right? Let me check that again. 8. 8 minus 1 is 7. There's a positive 7, but we're doing minus the middle one, right? Remember that? 8, excuse me, -8 minus 3. Wait, oh, sorry. Negative, 6 minus 2. Yeah, sorry. It's 8. Yeah, that's why I told you to check me on it. Okay. 6, let me just say that again. 6 plus 2 is 8. That's true. Okay. All right. So I think we're good. That's the cross product. Let's just check it real quick. The dot product. 2 times -11 is -22 plus 14 plus 8. Is that 0? -22 plus 14 plus 8 is 0. So we can check with the other one too, but I think we got it. All right. So now I think we got game over here. What's the equation of the line? X, Y, Z is equal to 2, -1, 2 plus t times this. Or any scalar multiple times this would be fine. So there it is. That's a line that passes through the point 2, -1, 2 and is perpendicular to both of the other ones. Pretty cool, right? Anyway, this is only like one of many questions we could ask involving these lines. Interesting questions that we could ask, right? What other interesting questions could we ask? I'm just thinking off the top of my head. Someone could ask you like about distances between points on lines, and then you could use the distance formula in 3 dimensions, you know, or find the magnitude of the vector. There's just so many fun things you could do here with vectors in 3 dimensions. Okay, let's return maybe to finish the example I think we didn't get to yesterday, which was on this PowerPoint here. Yeah. So we were talking about, and I don't know, maybe after doing the homework, maybe it's not worth doing. So maybe you're good. I think we described the process. But I thought it would be good to actually like work this one throughout. You know, it won't take very long, and then you know, you can know you'll be right. Huh? Yeah. All right, so I think we got to the point where yesterday we wrote down the two equations, didn't we, for Ashley? Ashley's baseball experience. So I'm just going to copy this down. You can catch up to me here. You already have it in your notes probably, right? 125 cosine 35 times t and negative 16 t squared plus 125 sine 35 times t plus the initial height 4. So that was our set of parametric equations. And now we're ready to like ask this question. I think we got far enough to say yesterday that we'd like to figure out when this hits the wall. Excuse me, when x equals 400. So we'll say what that is. And then we said we're going to plug that value in, whatever value we get. We're going to plug into the y function to find out how high the ball was at that point, and ask, is that a number greater than or less than 25 feet, right? So that was like the goal here. Let me pull up my calculator and just maybe show you some calculator skills that might help aid us in this process. Oh wait, I need this in parametric mode here. The other thing I'd love to be able to do is show you a picture of this as well. Let's like plot it. I don't know if you guys got a chance to do that. So maybe we do that first. Let's see here. 125 cosine of 35. How did that happen? Times t. All right. It's all good. All right. Negative 16t squared. You try and use the giant calculator. You'll see. All right. Plus 125 sine of 35 times t plus 4. All right. I would like to actually see this happen. So I don't know. Let's make t go from t 6, something like that. And x min is 0 to, well, 400 at least. How about 450 or something? So we get all this action happening. I have no idea how high it's going to go. I could like make some predictions, but I don't know. So try 50, and maybe that's too little. I of course need this to be a ball. That'd be the most fun thing to do. Maybe I'll make it with a ball with a trail. I'd like to see how this goes. So let's watch the ball go. That was anticlimactic. Okay. T step 0.1, and mode needs to be in degree mode. Let's get everything right here. Okay. What? I didn't actually press it. Respond to my demands, please. I wasn't quite high enough. There it comes. Okay, so we could actually find the maximum on that curve if we wanted to be more precise, I guess. Could someone find a good one? 75, maybe? Will that do? Still not quite high enough. How about 100? 76. 76? All right, we got the path there too. How can we get a wall drawn? Just for fun, it would be kind of fun to draw that wall, wouldn't it? Let's put in a second set of parametric equations, the wall, if we can do it. The wall is 25 feet high. Can we get something that... Now, we're graphing, maybe, I have an idea. Can we get a line, maybe, where x is 25, always, and y goes from, starts at, 400. Y starts at 25 and then goes down from there. Do you think that would work? Just for fun? Okay, let's see what that looks like. That wasn't very exciting. Here. Let's make it, yeah, 5t or something something a little faster there. And we already think we... Whew. Huh. That was pretty exciting. All right. That was obviously it's. I think we kind of know just from the picture, but the picture's not like very satisfying from a mathematical perspective. Especially if this had just barely skimmed it, we might have some questions in our mind. You know. All right. So I got distracted. What are we doing? We're gonna ask what is 400 divided by 125 cosine of 35. Make sure your calculator's in degree mode. And we get 3.9 seconds. Did you guys get that too? Okay. Store the value. Make sure you use it actually again. Here's another calculator skill I think you'll like. If you get vars, y-vars, parametric, y1 t of second answer. There we go. We get 39.9. Did you get that? So that's nice, maybe nicer than having to type it all in. If you already typed it in once, maybe you don't have to type it in again. So 3.9 and 39.9. So we can certifiably say the thing we've already said. It clears the wall by 14.9 feet, like with lots of room to spare, right? That's pretty cool. We could do that. So I think there was some, like there's a castle one, or I can't remember. There's some, they're interesting. Or did they do another baseball one? All right, everything's baseball. All right. Softball, something we can do. Okay, so I don't have anything else to say about parametric applications. We kind of hit those. I just wanted to like show you some cool calculator stuff from yesterday. Okay, next order of business would be to do whatever you guys want to do. I don't know. Do you have? Is there one in particular from past homework that would be good to go over? I'm trying to do something from another PowerPoint that we didn't do. Would be a good thing. I already put up solutions to, I think, to homework 5 and 7. So maybe you already have your questions answered about homework 5. Is that a good place to go, or what did you guys? Do you want to talk about homework 7 some more? What do you want? Or from last night too. Homework 6. You have burning questions from last night? Let's do it. I gotta find my homework 6. Okay. 51, I hear some people say. Is that what I hear you say? 45. All right, let's do 51 first, and then we'll go from there. I think if am I creating this grid, or is this the grid they gave you in the problem? I don't know. They want a Ferris wheel, 35 feet in radius. And we're out here at this point, starting like at the midline, and we're rotating clockwise, counterclockwise. And this distance here is 15 feet along here to the bottom of the Ferris wheel. And we're also told that we make 1 revolution every 12 seconds. Do I have all the information captured appropriately? I think I do. Do you agree with the way it's set up? Did they tell you to set it up with the origin here? I don't know. Or they suggested that somehow? I don't know. I mean, whatever. It's arbitrary wherever we put our coordinate system, but let's all agree to something, and maybe we all agree to this. If that's what we agree to, then so I have some questions now about the motion of this particle, and we can watch this happen when we plug it into our calculator afterwards if we get these right. Okay. The height of the Ferris wheel is y, right? And the height is modeled in exactly the same way. Let's just forget about x right now. We've done this before. The height of the Ferris wheel at time t. It's like a problem from last semester, isn't it? Perfect. Let's just review. So what's the amplitude? 35. How high is the Ferris? How high are you? Let's see. I might do. You could do it a couple different ways, but like let's actually zoom in on this a little bit here. How do I make a circle? I actually do this. I want to make this more precise here. How do I not make a circle? There we go. Okay. If you live right here on the circle, right here, can you help me figure out what your distance from the ground is? This piece, I know already, is what? I haven't actually said it yet. Is 50. I think there'll be a plus 50 at the end of this thing. Okay. What's this piece? Keep in mind that this is 35, and this is some angle. What will that be? What will that piece be? How do we find that? If this is an angle theta, what is this piece? It's 35 sine theta, right? All right. So so there's a little more to the story than that. But if we knew the angle, that'd be good, right? If you could tell me the angle, this angle here, then this would be the height, your height, if you knew the angle here, right? Well, what time puts you at this angle? We're making 12 revolutions per second. So what's the conversion from time to angles here? Don't we start here? So at 0 seconds, we're, oops. At 0 seconds, we're at 0 degrees. And at 12 seconds, we're at 360 degrees, or 2 pi radians. You want to do this in radians? So, so what's the rule that turns 10 seconds into angles? You want to put something else in here in between? How about 6 and pi radians? So what belongs in here in terms of t? What's the rule? Take the time and do what? I mean, this is also just what we did last semester. What's the period? What's b, you know? Yeah, so what goes in here? Pi over 6 times t. Let's just check that works. Does that put us at the right angle at the right time? If you plug in 0, you get 0, and that's definitely the height we need. If you plug in 12, that puts us at 2 pi radians, doesn't it? So let's actually plug that in here. Pi over 6t. That's just a discussion from last semester. And then, and I think we have y. Okay. It's just the height function that we modeled last semester. And then what about the distance from, what about this distance? How do we model this distance? Isn't that going to be the x model? What will that be? I mean, just think right triangle trig. What is that? 35. Okay, you're thinking too hard. It's 35 cosine theta, isn't it? And by cosine theta, we mean pi over 6 times t. Right? I think we did it, didn't we? Let's just confirm that this is doing the thing we want it to do. If t is 0, are we in the right spot? Plug in 0 and verify that we really are located here. Yes? Plug in 12 and verify that we're there again. Plug in a fourth of 12, plug in 3 seconds to verify that we are in fact right there. Are we? You plug in 3, you'll get pi over 2 in both of these. And the cosine of pi over 2 is 1, and the sine of pi over 2 is 0. My phone is talking. All right, let's actually graph that too and see what we get. I think this is good. I mean, it's almost like we wish we would have done this first semester when we were talking about this. And like, if we could have talked about parametric equations then, maybe the Ferris wheel problems would have been easier to see. By the way, the other way to think about this is what is this? What is the equation of? First, start with what's the equation of cosine t, sine t for x and y? That's the unit circle. What's the equation of 35 cosine t, 35 sine t? It's a circle centered at the origin of radius 35. What if we move it up 50? Well, now we have a circle up a little bit. All right, and then what does this pi over 6 times t do? Well, it just controls how fast that graphs. Regardless of what you put in here, you will get the circle, the correct path. It just depends on how fast it goes and where you start and all that. So we can play around with that, in fact. That'll be kind of fun. Let's make our window 2 pi here. I'm gonna have to put my calculator back in radian mode for that to work, though, I guess. Could have done it in degrees, though, I guess. But. This is not a good window here. How about negative, what would be a good window? 40 to 40? How about? What's that?
Oh, wait, no, it's sorry.
And how high do we ever get? 50 plus 35 will be 85, so let's have about 90. Okay. Are we ready to see this happen? Let's also zoom square. And wait, let's also change this to have a little ball, because I like the ball. Window. We did say the right, it is pi over 6, right? Yeah, if you plug in 2, yeah. Oh, T max needs to be 12. Yeah. Sorry. There we go. Is that going to give us the full circle? How would we get it to just graph like one quadrant? Could we do that too? We could just do, there we go, 0 to 12 seconds. You can make it go around a second time by doing 0 to 24 seconds. I don't know, that's kind of fun, right? You want to make it go around faster? Let's make it go around faster. What if the period was 6 seconds? Can we make that happen? There we go. Zoom that thing around. All right. I hope that was helpful. Like, go through a couple problems. Clean up a little bit. There's no additional.